Assalamu alaikum. Welcome to Learn with MSA. Today we're diving deep into something really core to programming. These are the fundamental building blocks for writing efficient code. We're talking about data structures.
You ever wonder about that? Why one app on your phone is just snap, lightning fast, and another one just chugs along and feels so sluggish? Well, the secret isn't always about having a beefier processor. Nope. A lot of the time, it comes down to something way smarter: how the data is actually organized under the hood.
So, here's what we've got on tap for this explainer. We'll kick things off with the basics, then walk through the different kinds of structures. After that, we'll figure out how to measure their performance and wrap it all up by talking about how to pick the perfect one for your project.
All right, first things first, let's get a really clear idea of what we're actually talking about here. At its heart, what even is a data structure?
The best way to think about them is as specialized containers. You see, in programming, data is just the raw material. Data structures are the tools we use to organize it all, and picking the right tool for the job, well, that can literally make your code thousands of times faster. It's a huge deal.
And it's not just about raw speed, it's about being smart. Good data structures help us use memory efficiently, find the exact piece of data we need in a flash, and honestly, they just help us write code that's cleaner and easier for other people, or even our future selves, to understand.
Okay, let's jump into our first category, and it's the most straightforward one: linear structures. Just like the name says, these are all about arranging data in a sequence, one thing after another in a nice, neat line.
So the most basic linear structure of all is the array. I love this metaphor. Think of a row of lockers. Each one has a number, right? And if you know the number, you can go straight to it. That is exactly how an array works. All the data is stored side by side in the computer's memory.
But here's the catch, right? There's always a trade-off. Arrays are amazing for getting stuff fast. You need locker number 5, boom, you're there. But what if you need to squeeze a new locker in between number 3 and 4? Oh boy, now you gotta move every single locker after that spot down by 1. That's a huge pain. And that inflexibility, that's the array's biggest weakness, for sure.
So what if you really need that flexibility? Well, that's where the linked list comes in. Forget the neat row of lockers. A linked list is more like a scavenger hunt. Each piece of data, we call it a node, also holds a little clue, a pointer, that tells you where to find the next item. The data can be scattered all over memory.
And this table really just lays it all out. This is the big choice you have to make. Do you need the super fast direct access you get with an array, or do you need the easy flexibility to add and remove things that a linked list gives you? You really can't have it all, so your decision has to be based on the problem you're trying to solve.
All right, next up, the stack. This one's super intuitive. It works on a simple idea: last in, first out, or LIFO. Just picture a stack of plates. You put a clean one on top, and when you need a plate, you take the one from the top. Simple as that. Your browser's undo function? That's a stack.
Now, the stack's close cousin is the queue. And instead of last in, it's first in, first out, or FIFO. This is just like any line you've ever stood in. The first person who gets in line for coffee is the first person to get their coffee. It's all about processing things in the order they arrived.
Okay, so lining things up is useful, but let's be real. The world is way messier than that. A lot of data has complex, interconnected relationships. So for that, we have to go beyond straight lines and enter the world of nonlinear structures. A tree is the perfect way to represent any kind of hierarchy. Just think about the file system on your computer. You've got folders inside of other folders, right? That's a tree structure. And this specific one here, the binary search tree, is a genius way to keep everything sorted, which makes searching for a specific file incredibly fast.
And for the most complex networks imaginable, we have the ultimate tool: the graph. A graph is just a bunch of points, or nodes, connected by lines or edges. And trust me, they are everywhere. A social network is a classic graph. You and your friends are the nodes, and your friendships are the edges connecting you. Google Maps? It's just one giant graph of cities and roads.
So we have this awesome toolkit now, right? All these different structures. But how do we decide which one to use? How do we actually measure if one is good or better than another for a certain task?
And when we say fast, we're not just talking about getting a stopwatch out. What really, really matters is how the performance holds up as the amount of data gets bigger. Does our solution stay speedy, or does it completely grind to a halt when you throw a million items at it? And that is where this thing called Big O notation comes into play. You can think of it as the universal language that programmers use to talk about efficiency. It's not about measuring speed in seconds or milliseconds. Instead, Big O tells you how the performance changes, how it scales, as your input size, which we just call n, gets bigger and bigger.
This table right here is basically our cheat sheet. O1, or constant time, that's the dream. It means it takes the same amount of time no matter how much data you throw at it. But down at the bottom, ON squared, or quadratic, that's considered poor, because the time it takes just explodes as you add more data.
And this chart just makes it crystal clear. I mean, look at how that ON square bar just skyrockets compared to the others. Choosing a data structure with a better Big O is absolutely the key to building apps that can scale and handle tons of data without collapsing.
Okay, let's pull it all together now. We know the structures, we know how to measure them, so let's make a simple, practical guide for when you should use each one.
Here it is, the main takeaways. If you need to grab things by their position all the time, use an array. If you're constantly adding and removing stuff, a linked list is your best friend. For anything that involves reversing actions, like an undo button, go with a stack. For anything with a hierarchy, or if you need super fast searching, a tree is the way to go. And for those instant dictionary-style lookups, a hash table is simply unbeatable.
So I'll leave you with this one last thought. The next time you're scrolling through social media, or you're pulling up directions on a map, or even just hitting that undo button, just take a second. Think about those incredible, invisible structures working tirelessly behind the scenes to make it all feel so instantaneous. It's pretty amazing when you think about it. Thanks so much for joining me.